In our previous session, we learned about the definition of vectors. Today, let's explore three operations involving vectors. First, scalar multiplication. Consider the vector u. What is the vector 2u? Yes, you simply multiply each component by 2, doubling the length of the original vector. Now, for another vector v. What is the vector negative v? Correct, it reverses direction, as each component is multiplied by -1. This is what we referred to as the opposite vector in our previous lesson. Second, addition of vectors. Move the vector u horizontally and vector v vertically, forming a parallelogram. The diagonal of this parallelogram represents the sum vector. To obtain the sum vector, you simply add the x components together and the y components together. In this case, the components of sum vector is 4 and 3. This method is known as the parallelogram method. Let's explore another method. Move the tail of vector v to coincide with the head of vector u. Then, connect the tail of u to the head of v, and the resultant vector is the sum vector. The calculation results in the same outcome as mentioned earlier. This method is referred to as the tail-to-head method. Third, the dot product or inner product of vectors. Consider two different vectors, u and v. To find the dot product, multiply the corresponding x components and y components, then sum them up. In this case, u dot v is 5. Remember some fundamental properties of the dot product. The dot product can be used to determine the angle between two vectors. Let's say we have two vectors u and v, and we introduce a red vector w connecting the two vectors. Using the tail-to-head method, we have u plus w is v, which implies w is v minus u. Let's denote the angle between u and v as theta. The three vectors form a triangular shape. What can we use in this case? Yes, that's right. Since the lengths of the sides of the triangle must be scalar values, we express them in terms of vector magnitudes. Using the property of vectors mentioned earlier, the dot product of the same vector is equal to the square of its magnitude. We expand the left side. Compute each dot product step by step. Expand both dot products on the left side, similar to the distribution. Remove parentheses from the left side and simplify. The dot product uv is equivalent to vu, so we rearrange it as 2uv. Utilizing vector properties, we transform the dot product of the same vector into the square of its magnitude. Common terms cancel out from both sides, resulting in a simplified expression. In summary, we derive a formula for the angle between two vectors that we will frequently use. Now, let's use this formula to find the angle between the two vectors u and v we discussed earlier. In the numerator, we have the dot product of the two vectors, and in the denominator, the product of their magnitudes. Simplifying, we get the square root of 2 over 2. This value is something we often see in a special right triangle. That's right, it's 45 degrees. Therefore, the angle between the vectors u and v is 45 degrees. See you next time.